So this is the last lecture on ideas of the book of Eichwidler, where she was talking about Pascoletti-Serafini. But Pascoletti-Serafini in 2 dimensions, we have a restriction lemma. I mean, a theorem or a lemma that says that you know where to go, or where that if you, for example, try to choose A in certain direction or certain areas, then it's enough. You don't have to find A in the whole space. But in 3 dimensions or more, we don't have any such theorem, and so we should go to other ideas. And for example, in normal boundary intersection, which I will talk about in the next lecture, you will see that we have a structural and better approach to handle with them. Even there is a better idea. I mean, the recent book of Christian Temer, she used. She looks at everything as a functional. So instead of Pascoletti-Serafini is not a functional, but you can define functional, such as what we do in shortage function of Professor Chris Kersten's. So let's move, and so we proved this lemma that for individual problem we have a minimization. We find A and T, and this is the polyhedral cone. And now for Bicriteria, we only have 2 objectives. We minimize this, and this is just an example. We want to prove lemma 2.15. So if this is our cone, this is the ordering cone, we want to prove these 2. And we prove this by saying that first, so the problem is y is in R2, and Li transpose y is greater than equal to 0, and I is 1 and 2. So x1 bar is a minimal solution of minimized L1 transpose f of x, and also x bar 2 is a minimal solution of L2 transpose f of x. So the theorem says prove that L1 f of x, L1 transpose f of x is between L1 transpose f of x bar 2 and L1 transpose f of x bar 1. And also L2 transpose f of x is between L2 transpose f of x bar 1 and L2 transpose f of x bar 2. Because if we prove this, the second one is similar, so I start off by proving the first one. So we can use that. We can say that immediately. We can say that L1 transpose f of x is greater than L1 transpose f of x bar 1, and L2 transpose f of x is greater or equal to L2 transpose f of x bar 2. And we prove by contradiction. We say that suppose there is a point x inside M f of omega and k such that L2 transpose f of x is greater than L2 transpose f of x bar 1, and L2 transpose f of x minus f of x bar 1 is greater than 0. And so we can immediately say from this one that yes, L1 transpose f of x minus f of x1 bar is greater than 0. And we can immediately say that f of x minus f of x1 bar is inside the cone, excluding 0. And so this is a contradiction, and we can say that L2 transpose f of x is less than equal to L2 transpose f of x1 bar. And so we can just use this idea to understand that if you use A and T, there is like a projection of that in direction R, and we can show that we can find the hyperplane and we can restrict on that hyperplane. We know exactly from start to bottom, we know exactly, but in more than 2 dimensions, we don't know it. But let's prove theorem 2.17 for the case of m is equal to 2. And for that, we want to say that we want to prove that if x bar is inside m of f of omega and k, there exists a parameter a and t bar inside R such that t bar is equal to b transpose f of x bar minus beta divided by b transpose R, and a is equal to, we already know that, t bar R, so that t bar and x bar is a minimal solution of SPAR. But this is from theorem 2.11. So the parameter lies on the line segment between a1 bar and a2 bar. So we can write A mathematically as saying that this is a bar 2 for any lambda inside this 0 and 1. And we can just substitute it. A is f of x bar 1 minus t bar R, and a bar 1 we can substitute for that. F of x bar 1 minus t bar 1 R plus plus 1 minus lambda f of x bar 2 minus t bar 2 R. And if the efficient set consists of 1 point only, then it's easy. Then it is either lambda is equal to 1 or equal to 0. Otherwise, we can use that lemma, I think 2.16, that says that L1 transpose f of x bar 1 is less than L1 transpose f of x bar 2, and also L2 transpose f of x bar 2 is less than L2 transpose f of x bar 1. And reformulating it, we can reformulate it by saying that f of x bar is equal to lambda f of x1 bar plus 1 minus lambda f of x bar 2 plus t bar minus lambda t minus 1 minus 1 minus lambda t bar 2 R. And we can now set the condition. For example, if this is the case that this one is less than 0, what happens? If that is greater than 0, what happens? And we can come up to some conclusions as I've written here. So this is the rest of the proof. It's very easy. And so